Hey guys, welcome back to this tutorial on Microsoft Robotics Developer Studio, and this is part 2 on this video series. So I hope that you guys must have enjoyed part 1 where we covered the installation and setup of MRDS and saw the components that get installed once you have it on your system. We also had a brief look at the prerequisites and also had a taste of the visual simulation environment where we tried to run a simple block robot using a dashboard and experienced how realistic the simulation environment that accompanies MRDS feels. So in case you guys have any questions or comments, please feel free to leave in the comment section below and I'll try to respond as soon as possible. So what are we going to cover in this part? I decided to cover a little more conceptual overview of each of the key components involved while developing robotic applications using MRDS before we dive into the code and the practical details. So without any further ado, let's get started. So the first component that tops our chart is CCR, which stands for Concurrency and Coordination Runtime. And as the name suggests, it provides a concurrent execution model for the code that comprises the services that we develop using the MRDS. CCR makes it easy to handle asynchronous input from multiple robotic sensors and output to motors and actuators. So because this is in the context of MRDS, that is why we are alluding to the robotic sensors and motors and actuators. But in a sense, these are just the services that we develop while writing the robotic applications using the Developer Studio. So it handles the inputs and outputs asynchronously, so the code is basically run parallelly. And it also provides a coordination mechanism using an event-driven notification paradigm. So whenever there's an event in one part of a service, it simply forwards that data or that message to the subscribers interested in listening to or getting the notification for that event. CCR manages all tasks passed to a call to activate. CCR is a concurrent task dispatch infrastructure on which DSS is built. So activate is a code construct provided by CCR framework that we use to assign the tasks to be run on the CCR. The next component on our list is DSS, that stands for Decentralized Software Services, and which is by far the most important component of MRDS. It is so because whatever we write is essentially a DSS service. So when you write applications using MRDS for your robotic hardware, you essentially compose DSS services that run independently of each other in a loosely coupled fashion and simply exchange messages to provide functionality. And we'll see that in the upcoming example in the next part of this tutorial. So DSS uses CCR to provide a REST-based service-oriented model for using resources or services. So DSS services use a REST-based model for communication, and this is pretty synonymous to the REST APIs that a lot of web developers might be familiar with in today's world. DSS solves some programming challenges that address robustness by providing loose coupling, as I just mentioned, and composability, because we can use these loosely coupled services as they have no real-time execution or compile time dependencies to compose new services. It also solves the programming challenge of observability by exposing the service state, much like the WCF, and which is like identifiable by a URI to be monitored. DSS service use DSSP, which is a SOAP-based protocol for communication, and it also uses HTTP, which is why we would be able to monitor the DSS service in the DSS control panel using a web browser. DSS provides an event model driven by state changes, which is actually supported by CCR. So proceeding, here's a little more insight on the DSS services. So what is a service in the context of MRDS? So if I were to give an example of a service in the MRDS context, I can think of a range measurement service. For example, there is a range sensor on the robotic hardware, and your application wants to utilize the data from the range measurement of the range sensor. So there will be a range measurement service that would be running on the robotic hardware, and then your service, which you'll be developing, will receive notifications from the range measurement service. So like this, these services actually communicate and share functionalities between themselves in an MRDS application that we develop for the robotic hardware. We have seen DSS before. DSS facilitates bringing services to life in an MRDS application. And this code is taken directly from Microsoft. It's a primary design goal of DSS is to couple performance with simplicity and robustness. This makes DSS particularly suited for creating applications as compositions of services regardless of whether these services are running within the same node or across the network. So DSS hosts these services inside something called DSS node, which acts like a segregated execution container, and the services execute inside of these containers. It doesn't really matter where in the world these services will be running on the DSS node. They would be able to communicate to the other services using the simple REST-based or REST-style messages. So writing an application using DSS is a simple matter of orchestrating the input and output between a set of services. This is pretty much the gist of application development using MRDS, because as we mentioned that everything in MRDS is a DSS service, it all boils down to the fact how well you're able to orchestrate the input and output, basically communication between those set of services. So services represent the interface to software or hardware and allow you to communicate between processes that perform specific functions, as we just talked about. So proceeding, here's a short and small schematic representation of how these components fit together. So CCR forms the base layer on which sits DSS. So DSS has something called DSS nodes that act like segregated execution containers, as I discussed before, and the services are hosted inside of them. The services can communicate between themselves or with services running on other DSS nodes, and it does not matter where in the world the other DSS service will be running. These services may still be able to communicate using the simple REST-style messages, as we discussed before. So the next component that I would like to touch upon is VPL. Now this is something new because we did not talk about this in part 1 or even in part 2 thus far. VPL stands for Microsoft Visual Programming Language. Though we'll not be using VPL in developing our robotic applications, but it's good to know that something like this exists. So VPL enables anyone to create and debug robotics programs very easily. Just drag and drop blocks that represent services and connect them. It is also possible to take a collection of connected blocks and reuse them in a single block elsewhere in the program. So it's pretty simple and straightforward. It's like a visual programming environment. You have this toolbox over here from where we can simply drag and drop the code constructs into this programming area and construct your services. This essentially composes a DSS service. So as you can clearly see, the GUI-based programming environment called VPL is essentially good for non-programmers because all you have to do is essentially drag and drop these code constructs on this programming area and build your logic. As the sentence already says, that it's possible to take a collection of connected blocks and reuse them as a single block elsewhere in the program. So it definitely is good for rapid prototyping because it's easy and fast to construct basic programming logic for your robotic applications. However, we will not be using VPL for developing our examples in the upcoming parts of this tutorial. So proceeding is the next component on the list, which is also our favorite, called the visual simulation environment. We briefly glanced over the simulation environment in part 1 of this tutorial, where we tried to run a basic block robot controlled using a dashboard. And we saw how realistic we got the feedback when we tried to be rigorous with the robot that rubbed against the wooden floor and toppled down. So I think anybody would agree with me that for a good robotics software, it's imperative to have a robust and realistic simulation environment because nobody wants to expend time and effort in developing robotics hardware just to be able to realize simple or initial robotics applications. A good simulation environment also plays a key role in testing the robotics applications properly. So the VSE easily simulates robotics applications using realistic 3D simulated models. Microsoft Visual Simulation Environment includes NVIDIA physics technology, enabling real-world physics simulation for robot models. Physics simulations can also be accelerated by appropriate NVIDIA hardware such as GeForce graphics cards or even simple Intel accelerators. So in case your system has basic Intel accelerator graphics unit or the GeForce GPU or ATI Radeon, you should be good to go to run the visual simulation environment smoothly. So here are 2 screenshots. On the left hand side we see a very nice apartment model that would definitely provide a nice realistic environment for our robotic hardware or the robotic application to be realized. Alright, so before concluding this part, let's have a brief look at the outline of a DSS service itself and the parts that comprise it. So here is a schematic diagram taken from Microsoft documentation itself that represents the parts that comprise of a DSS service and how it actually appears in terms of its components. So the first component of a DSS service is a service identifier, which is used by the DSS runtime to discover and load a service. A service identifier is a simple but unique URI that is responsible for uniquely identifying a service. The second part is a contract identifier, which is responsible for uniquely identifying a contract exposed by the service. A contract is actually synonymous to the contracts exposed by a WCF service for those who know about it. So, yeah, one more thing. A contract identifier or the contract is used by the CCR to build the proxy assemblies for that service, because in the MRDS development model, whenever we develop new services, we always reference the proxy assemblies and never the original assemblies themselves. We'll see that in the example in the next part of this tutorial. So the next part is a state. Now, a state is nothing but the specific instance of a service object at a given point in time. A state is useful when serializing the state of a service so that its data can be used by or consumed by other services. The next part is a list of partners, which is nothing but the other dependent services or dependencies that this service requires to be running in order to function properly. Last but not the least is the ports. And there are two types of ports. First, the main port and the other notifications ports. The main port is also sometimes referred to as operations port. Let's take the example of the measurement update service. So, for example, the measurement update service defines the operations of providing the measurement updates and would accept messages of type updates or measurement updates on its main port. The service handlers are the handlers responsible for handling the incoming message on the ports. The same goes for the notifications port. There are notification handlers that receive or handle the notifications that are received on the notifications port from the other services to which this service would have subscribed to receive the notifications from. So that's about it for this part of the tutorial, guys, and in the next part we'll be creating a simple DSS service and then realize how all of these components and concepts fit together in the code practically. So till then, have a nice day and stay tuned. Thank you for watching.